Hey everybody, Mr. Smith here. Welcome back. In today's slide deck, we're going to tackle vertical motion. This topic is either really easy or it can be really tricky unless you pay attention to the one fact and the two skills that I'm going to give you in this slide deck that can make it easy and fun. So first things first, you've been to the amusement park and I hope you've had this kind of experience here.
Whoa. Get your hands to the side.
No.
Whoa. Go, go, go! Whoa!
The biggest thing that I want to give you that's a fact is this, and that's that you in your gut have a built-in accelerometer. You can tell if you're accelerating. It's really gross, but it's simple and it's true. Here's the story. If you're in a roller coaster car gets pulled down by the force of gravity, and so it accelerates towards the ground. Your body is anchored by that harness that you wear on one of these steep rides, and that means that your skeleton is also anchored and pulled down by the force of gravity, and you keep track right with the car. Here's the story. Your guts, literally like your stomach and everything else that's loose and kind of jiggly inside the middle of your body, that's not really tied down to your skeleton. And because that stuff has mass, it has inertia. And that means it likes to go steady speed in straight lines. So what has to happen, what does happen, is that as you accelerate towards the ground, your body is always tugging on your guts, going, come on, come on, come on, go faster. And your guts are kind of like, I'd like going steady speed, thank you very much. And your body's like, no, go faster. And the feeling that you get of acceleration in your belly is the nerves that are attached to your gut going, hey, somebody's pulling on us. True story, okay? So fact number one, check out how it applies to this situation. So what you see here is a perfect example of you not accelerating and you accelerating. So here's what I mean. If you're in school in a desk, seriously think about it. You don't have that feeling in the pit of your stomach that you get when you're on a roller coaster. If you've ever had the chair pulled out from underneath you though, or you've gone skydiving maybe, then you do have that feeling of free fall that I just talked about. So that's the first fact. Please understand, you would know it if you were accelerating. Human beings are sensitive to acceleration. What's crazy is that we're not really sensitive to speed. So we can talk about that more in class. What I wanted to get to right now is the first of the two skills that we wanted to talk about. Here it is. The first skill is just to recognize, are you being supported by an object or aren't you? So in vertical motion, there's only two kinds of problems. There's ones where you're supported maybe by a chair or by a floor, and you should know, okay, I'm not being accelerated. Here's why. When you're being pulled down by gravity, which always is there, when you have a chair present, there's a second force which comes out of the chair called force normal. Now, normal is a math word that means perpendicular. And what it's perpendicular to is the chair, if you look at it. This thing also works. If you've ever tried to lean on a wall and maybe push the building over sideways, you realize you can't do it because a response force from the wall pushes back on you. And what's cool is this is automatically equal and opposite to the applied force of gravity. So what you're going to see me do in example after example is work with up forces and down forces. The big thing to realize though is that when you have a chair or a floor, this force normal is automatically going to be equal to the weight. And when I have up and down forces equal, that means they cancel. And the F net is 0. And when F net is 0, I have no acceleration. Okay? And the simple comparison, real quick on this one, if you do have a force of weight pulling down on you and you're just a cartoon character hanging in space, there is no up force acting on you because there's no floor there. And what happens is you accelerate to the ground. And your velocity could be whatever it wants to be, but the acceleration is going to be pretty darn close to minus 10 meters per second per second. Okay, so first skill, recognizing the problem. Am I sitting on a chair or a table or a desk, or aren't I? Okay, second skill, really straightforward. If you do this next thing I'm going to show you, and you do it every time, these problems are going to be simple for you. Here's what it is. You key in on the mass. And I'm going to give you a simple formula. I'm going to draw a downward arrow and write down Fg. That stands for force of gravity. If you'd rather call it weight, be my guest. Both of those are the same thing. force of gravity equals weight. And there's a very easy formula that you can use that says that weight equals mass times acceleration of gravity. And we'll talk in another slide deck about where that really comes from. It's actually a little cheater formula that I'm going to give you right now, but it works and it's true and it makes your problems easy. So what do? I key in on the 100 kilograms. I know that the acceleration of gravity right down here near the surface of the Earth is very close to minus 10 meters per second, and I do this math first thing right away. So what's the second skill that's so important? Take the kilograms, multiply it by minus 10, put it on the weight right away. And then what you can do next, after you do that, is worry about the other arrows. So if this one says he leaps from his plane, he has no downward velocity, what's his acceleration? Well, if he has no downward velocity yet, he's just leaped out of the plane, then he's not smashing into any air. So he's just for an instant like that cartoon character that's suspended in space. And what happens is there's no force of wind resistance acting on him because he's not smacking into any air. And what I've got is Newton's second law, F net equals ma. You're going to see me add up all the forces. Well, there is only one force at this occasion. Minus 1,000 newtons equals 100 kilograms times the A. And what I get in this one situation is I get right back again the minus 10 that I just put in to calculate the weight when I solve for acceleration. Okay, so let's go through and do a little bit more complicated example, and you'll see how it works the same. So now he's fallen a little bit, and what I'm going to do is exactly the same thing. Skill number 2, very important. Automatically take weight equals mass times acceleration of gravity. We already did that work. It was 100 kgs times minus 10 meters per second squared, and I put that number down. Don't ever even worry about it. Just don't even think about it. Just take mass times gravity, put it down for the weight, and then move on. Now, if I read the rest of the problem, wind resistance of 400 newtons acts up on him. And so in my way of doing these, I always make the downward forces minus and the upward forces plus. And that's where this formula, F net equals add up all the forces and it equals ma comes into play. So what I do is I add up all the forces of minus 1,000 newtons plus 400 newtons equals m times a, and I work that through and I solve for a. So over here is minus 600 newtons is the net force. It's the sum of all the forces, and it also equals ma, and what I get from this is the acceleration equals negative 6 meters per second. So what happens is as you fall, you start smashing into air and you don't accelerate freely anymore. Your acceleration isn't minus 10 meters per second. You're still speeding up, but just not as good. Okay, now he's fallen further, and what's the story now? Don't even spend time thinking about it. Take his mass, multiply it by minus 10, pencil that in right away, and you'll save yourself the biggest headaches that people get in this topic. Now, I read the rest of the problem and I realize there's wind resistance, so I draw that arrow in, and they tell me this is 1,000 newtons. Okay, that's good. So I put in 1,000 newtons, and can I get his acceleration? You bet. Sum of all the forces is what F net is, and F net also equals ma. Minus 1,000 newtons plus 1,000 newtons equals 100 kilograms times A, and what I get is 0 equals 100 times A, and A equals 0. So has he stopped? No, not even close. For you and me, like we talked about, he's probably falling around 120 miles an hour. He's smashing into so much air per second that the air pushing up on him is actually equal to what he weighs. Amazing. And so what has happened is he can't accelerate anymore unless he turns his body into a pencil, maybe, which would maybe be not suicidal, but that's one way you could make yourself accelerate again, is give less of a target to the air. Finally, let's go take a look at another example, different graphic, because this one popped his parachute. So let's go ahead and do the same thing, though. He's 100 kilograms, and we've got minus 1,000 newtons. That is equal to the weight. And they tell me that he pops his parachute, and now the up force is bigger than the down force. What's the up force? it's equal to 2,000. And that would be the force of air resistance or force of wind resistance or something like that. And I don't think I've been labeling those, but it's okay. So what I'm going to do, sum of all the forces is what F net is, equals M times A. And do what you've been doing. 2,000 newtons plus negative 1,000 newtons equals 100 kilograms times A. And I go ahead and trace that through. So A is going to be, check me out, positive 10 meters per second. And what does that mean? He's back in free fall? No, not at all. Now what's happening is the negative speed that he has, it's going to get chopped down real fast, because this number, that's about 20 miles per hour per second in the upward direction. So if that makes sense, he's going to lose his negative speed very quickly and get a more comfortable lower speed. Okay, and here he is traveling at that more comfortable lower speed. So here's the situation. Read the problem carefully. If they say anything about constant velocity, what you're going to find is a situation that you've seen before. So weight, as always, equals negative 1,000 newtons. Upward force is unknown, but here's what we do know. If they say the speed is constant, you should know that that means acceleration equals 0. And I bet you can see this one coming. So I'm going to call this the force of wind, or Fwind. And I'm just going to go ahead and write down Newton's second law, but I'll bet you know what's going to happen here. Add up all the forces equals ma, so force of wind is an unknown, plus negative 1,000 newtons equals 100 kgs times acceleration. The thing is, acceleration is equal to 0. And so since this whole right side of the equation's got to equal 0, this whole left side equation has got to equal 0 as well. Force of wind equals 1,000 newtons. And equal and opposite. So if you're falling at steady speed, you're basically in your gut feeling the same feeling you had as you sat in the classroom. Or if you're driving in a car at steady speed, or any of those kind of constant speed situations. Anyway, bring questions to class. Good to see you. Take care of yourself, and we'll see you soon. Bye-bye.